Hi, and welcome to our first session here on feature selection. So this is a pretty, I would say, high level, not too complicated introductory session on what feature selection is about, why we actually might be interested in that, so why are we not like using every piece of information that we have, and we'll look at a few simple examples and simple arguments why using too many features in a potentially unregularized predictive model might be harmful, even for prediction, certainly going to be harmful for reducing the complexity of the model and trying to understand it and analyze it. We'll also say what the difference is between feature selection and feature extraction, although the two things are quite related and we can both use them for dimensionality reduction. They do behave differently and they kind of also have somewhat different goals in mind, and then at the end we'll summarize what the different categories for feature selection methods are. So usually we categorize them into filters, wrappers, and embedded techniques, and especially wrappers and filters we'll then study more in detail in later sessions in this chapter here. Okay, so what's feature selection all about? Well, I guess it's about selecting features in machine learning tasks. So it's about finding a well-performing, hopefully small set of features for a given predictive task. So I don't know, maybe you have some regression problem, some classification problem, or some other form of a predictive task. And now the question is, can you find a small feature set which maybe even performs better in prediction or nearly as good as the full feature set, and which is hopefully not too large? And you can already see that there might be some form of a trade-off going on. So I guess this might not necessarily be, we're going to kind of now later write this down as an optimization problem, and we can write this down as a single objective optimization problem. We're just saying, well, let's go over all of the feature sets that are possible, all of the subsets of our features, and then find the one that's bad. I don't know, that's bad, that's best for predictive purposes, so maybe which behaves best under cross-validation, and we'll use that, and this essentially will be kind of our objective for when we construct and look at these wrapper type of feature selection algorithms. But we could also say something like, maybe we are okay with finding a feature set which is quite small and which is maybe even a bit worse than, the optimal set, which might be quite large, but because we like small feature sets, because they are associated with small costs in prediction, or because they give rise to models which are much easier to analyze. Feature selection is pretty crucial if you have high dimensional data sets which are quite noisy, which have a lot of noisy features in there of lower quality, where the chance of overfitting is quite high. So in a certain sense, you can also see feature selection as a, pretty expensive form of regularization. It can improve predictive performance. Why that is true or can be true, we'll study in a few minutes. And it certainly can enhance interpretability because it will help us identifying the most informative features, and it will also help us to analyze our fitted ML models, because if these models are fitted on a smaller amount of features, these models will be, of lower dimensionality, and I guess this makes it much simpler to analyze their structure and how they predict and how they model our given data set. We can now, of course, perform feature selection also based on domain knowledge, by tapping into the knowledge of domain experts, by looking at, studies of prior modeling on the same domain, on the same underlying, distribution. If we're happy, if we're lucky, there's some prior work, but of course here, and this does have its value. Here we'll rather study now data-driven algorithmic approaches, so we'll construct algorithms that figure out, based on our given data, what the most well-performing features are in this, if we construct such a set for selection. So maybe let's start by getting rid of this naive view first, that if we have more features, we potentially just have more information, and more information is always better. So we have better predictive performance, or at the very least, our model doesn't become worse. Because let's assume that we have, hundreds of totally irrelevant features, maybe totally noisy, totally bad, they don't help us at all. for predictive purposes, then I guess as we are using, I don't know, machine learning, which is a totally cool, I don't know, magic tool for data analysis, this is no problem, right? Because, I don't know, let's say we have something like a linear model or whatever, then all of these features, the effects of these features will simply be estimated to be 0 because they have no value in prediction, right? And in a certain sense, the model will already get it right. It doesn't matter if we fit that on this super high dimensional data set. Turns out this is quite wrong, because numerically and like stochastically, these effects will not be exactly 0, and they will result in an error component in the prediction of these then quite high dimensional models, and all of these tiny errors will add up to something pretty bad at the end. So we also discussed that in the curse of dimensionality section, so this is kind of highly related. I also discussed this in the chapter on regularization. That is also highly related, and I kind of stole one example from this regularization chapter for us here. So here we have a pretty low dimensional feature space, so just like, I guess it's exactly a dozen features, but my data set is also very, very small sample size. So in comparison to the number of features, I still don't have too many observations. And I'm now also cheating a bit here. So I'm already ordering features in the order of their usefulness for prediction. So I did something like a filter technique, I think, if I remember correctly. So I kind of measured the correlation between each feature and the output, and then ranked them and ordered them in terms of their correlation and their usefulness. And now I'm fitting linear models to a one-dimensional feature input set, 2, 3, and so on. And what we can see here is that, of course, the training error monotonically goes down. So in a certain sense, this is also what we have here on the x-axis is model capacity, model complexity, and then training error doesn't monotonously go down. And for training error, this naive view here that more features is more information and we will always fit better, that's true. But we are interested in the prediction error, and that actually does go down in the beginning because adding in more of these features is actually helpful, but at some point overfitting takes over, and the test error actually goes up quite drastically. And pretty sure in the regularization chapter I analyzed this example here more in detail. Want to stop here for now and rather go on with the discussion of feature selection itself. So I've already, I think, hinted at the fact that if we have these high dimensional data sets, then very often we kind of already know or have to expect that many of these features might be quite irrelevant. They might be also redundant, so we might have the same information in there in certain subsets of features, and many of these features might be of quite low quality. Also, so this already gives us a reason to construct sparser feature sets, because for all of these reasons here, we might exactly get this overfitting effect if we don't regularize against that. And we could do that through feature selection. There might also be another quite realistic reason for why we want to reduce the amount of features in our model, because features can actually cost us something during prediction time. I mean, if we perform feature selection, as you will see later on, this can be a computationally quite demanding process. So we are paying something for that definitely in training time, or in model construction or model selection time. But this might be worthwhile because if we now later on deploy our model and then use it again and again and we predict on new data, it might be that we have to pay something for, the features have to come somewhere, right? We at the very least have to construct them. Maybe we have to measure them somehow. And this will take computation time. It will also take computation time in the model, but there might also be computational processes associated with computing the features, or we might have to measure them somehow in the real world, and this might cost us money. So using less features during prediction, might kind of be another further goal. And another reason is that many of the classical models usually assume that we have more data points than features. So some of these models actually fail if we are in these super high dimensional settings where P is larger or much larger than our sample size N. And then we have to do something. Of course, we can also use regularization, but we can also, especially if these spaces are so large, kind of have to also draw them down. Usually then we use these filter techniques that I will also discuss here in this chapter, just to make anything work. Yeah, right. We might be in situations where you have like millions or even more features, and then we just have to do something. So we maybe, I don't know, can squeeze our data set into memory or have our any type of, I don't know, smart learning algorithm actually do something in finite time on these data sets. Here's a little, I don't know, categorization of sizes of data sets. So, I mean, first of all, I guess we could discuss a little bit why we don't see these classical low-dimensional data sets that much anymore nowadays. I mean, we do see them, but okay, maybe I should explain these settings here first. So this is also not very canonical, so I kind of came up with this terminology myself here, but I think it's quite fitting. So we might call something a classical setting in terms of feature dimensionality if we have somewhere between, I don't know, 1, I guess that's kind of the lowest interesting number of features, between 1 and 100 features maybe, okay? And these scenarios, feature selection might be still relevant, might still be interesting to figure out. Like if I have 100 features, which is an, I don't know, well-performing, interesting small subset, if I can reduce it to like 3 or 4, still might make, I don't know, post hoc analysis of the underlying relationships much simpler, and this might still be beneficial to us. But I mean, in terms of getting much better predictive performance, usually this is very often not so interesting. And then we have data sets of, I don't know, medium to high dimensionality. Usually this is somewhere between 100 and 1,000 features, maybe between 100 and 10K features. And here, classical modeling approaches can still work quite well. But principal feature selection still helps in many cases, also helps us very often quite drastically by improving predictive performance. And then there are these high dimensional data sets where have beyond 1,000 or beyond 10K features. Nowadays they might go up towards, I don't know, 10 to the 9, 10 to the 10. So these can be extremely high dimensional. Maybe again, think about this curse of dimensionality session that we did here together. It actually is quite surprising that we can model in these spaces at all. Examples, so I don't know, traditional examples are, I don't know, microarray or gene expression data. So usually these are also these ugly scenarios where your P, so your number of features, is quite high. Maybe, I don't know, 10K, 50K, but we only have a few hundred of observations. I don't know, maybe 200, because I mean, this might be on, I don't know, might be studying, I don't know, the probability of suffering from a certain disease. And then you want to understand the relationship between genetic data and this probability of getting that disease. And very often these things are rare. And we cannot kind of magically make more data appear in these scenarios. Text categorization, so bag of word features are a second scenario. In this second scenario, usually these are not like these low sample size. So you can usually have lots of texts, but it's still going to be quite high dimensional. And in this first scenario where we have very, very few samples, but very many features, and this feature size here is much larger than sample size, we call these, well, the P much larger than N scenarios, sometimes written like this. Okay, maybe I didn't go through this here yet. So why are we actually nowadays seeing these data sets here and these much higher dimension data sets more often? Well, we now are able to measure basically everything pretty much automatically. So everything is now kind of a computer or a thing with sensors. Everything is connected to everything through the internet. And this makes data sets with extremely high dimensionality much more likely and available to us. On the other hand, very often for these classical data sets, I don't know, a couple of data scientists have pondered quite for a long time which information, which features actually make sense. So very often for these lower dimensional data sets, features are of a much higher quality. It's much harder to also, because of this, to overfit on them. But for these high dimensional data sets, it's not like, it's kind of searching also for the needle in the haystack, right? So there's lots of redundant, low quality stuff in there. And especially for these cases, feature selection makes a lot of sense. Or regularization, if you want to do that instead. Here I now want to contrast a little bit feature selection against feature extraction. So in this chapter here, I will mainly focus on, I will pretty much exclusively focus on feature selection, and we have defined that already. So here, if you have a bunch of input features, so feature selection creates a subset of these original features. So we cannot produce or select anything else of what's originally there in our given data set. Feature extraction, on the other hand, is usually also, this results in, the goal of this is dimensionality reduction, right? So I have maybe 1,000 features and I want to reduce this to, I don't know, maybe 10, 20, 100, depending on how well these sets work. Feature extraction, on the other hand, also tries to reduce the dimensionality of the input space, but it allows itself to be a bit more flexible, because what we can do for these lower dimensional features here that we're then going to use, these can be transformations of, multivariate transformations of our original features. So we can, for example, produce linear combinations of some input features, so we can even produce nonlinear combinations of them. And this means that kind of the meaning and the associated interpretation of these original features can actually get lost through these transformations. And we might have a much harder time interpreting models based on these extracted features. It also might mean that we are not saving anything in terms of having a lower amount of features during prediction time, because just consider that you are using one feature here, F1, you're just extracting one thing, but this one thing is now a linear combination of everything else everything what's in your input space, right? So you have to compute this extracted feature during prediction time, which means you have to still collect all of the original features and then do this linear extraction. On the other hand, feature extraction can actually work better in terms of using less features in your model, but give rise to lower generalization error. So maybe first of all, let's as I've already said, feature selection and feature extraction, they both are forms of dimensionality reduction. They both result in simpler models. If you're willing to call a model simpler, which has been fitted on this derived feature space, and you're kind of forgetting about that you also have to do the transformation for the extraction. Here are some types of pretty common feature extraction techniques. So there's PCA, principal component analysis, there's multidimensional scaling, there's manifold learning. So these are unsupervised techniques. There are also supervised things like a supervised version of PCA, which is pretty nice, or things like partial least squares and so on. Now, here is a hopefully instructive example. Maybe it's also not so surprising that if you're allowing yourself a feature extraction mechanism that can actually work better in terms of predictive performance, if you compare the reduced dimensionality of these two techniques. So here I have to plot it somehow. So my original space is just two features. I guess that's not too high dimensional. And my feature reduction is now just using one feature. So, and I have a binary classification problem with these two distributions here. I guess you can also quite easily see what I guess a pretty much optimal model would be. So it would be something like a hyperplane, right? Now my question is, if I'm restricting myself to a one-dimensional input space, how well can I model that through feature selection and through feature extraction? So let's maybe study feature selection first. So we just now projecting our data to one of the axes. So we can project on this guy here, and we can project also on this guy here. So if we now project it on x1, and if I project on x1, everything will still be normally distributed. So I get these two Gaussian bumps here, which have a certain amount of overlap, and I can now build a simple thresholding model on this feature of x1, which will probably threshold on x1 somewhere here around this point, and the overlap of these two Gaussian curves specifies how much of a generalization error I will see if I put this model to use. If I am allowing myself to perform some form of feature extraction, maybe by doing some form of PCA, then I could, for example, say, well, I don't necessarily have to project my data on one of the axes, so why don't I just project it on this axis? So projecting on this axis is a linear transformation of x1 and x2, and then I have one feature left, the projection here. So I guess most of the darkish green guys will be projected here, and the light greenish guys will be projected here. And I can now model in terms of this derived feature. And now, again, I get these two Gaussian bumps, but they are much farther apart, and my generalization error would be much lower. So guess it's your choice now whether you want to call that, I don't know, a lower dimensional model, because at the end it still uses both features, right? So if you kind of write that as a pipeline, you have to take your two original features and then do this linear transformation. And then you have a one-dimensional feature which you are going to model on, maybe again with the simple threshold model. Whether this gives rise to something that you like and is interpretable and is worthwhile to you, I guess largely depends on whether you can associate some meaning, some intuition with this extraction and this transformation. So how will the rest of the chapter here look like? So we'll now introduce different categories for feature selection. So we'll go through filters and wrappers, and there's also embedded techniques. So there's a very well-known paper, overview paper on feature selection by Isabelle Guyon, which came up, I think, I'm not sure whether she was the first to categorize it as such, but it's, I guess, the most well-known publication. I think there's even a complete book by her on the topic. And yeah, we'll kind of follow exactly the same path and the same categorization. So we'll start by describing what we mean by feature filters. So these evaluate or estimate statistically the relevance of features using statistical properties or statistical measures of dependence between univariate features or even feature sets and the target variable. We'll also study wrapper algorithms. These are usually to Ron Kohavi. He came up with them, I think, somewhere around the middle or end of the 90s in his dissertation. So these usually use a model to evaluate subsets of features, I don't know, on validation sets or under cross-validation. And then there are embedded techniques. With embedded, we just mean that the feature selection is somehow directly baked into a specific model. So maybe remember again how decision trees work. They already perform some internal feature selection. Or we've also discussed already stuff like L1 or L0 penalties. So the lasso, or I guess don't know a different better term for L0. I won't go through this here in this chapter because this is pretty specific to how these models work. I'm just saying that these things exist, and it's usually not a simple choice between what you should do, whether you should rather run a filter. So you do that usually on super high dimension spaces or an embedded technique. So this, I guess, depends a little bit on how well your model class works for your given data situation, and usually you do these on these medium dimensionality settings, although we have become also quite good with upscaling these types of techniques to quite high dimensional scenarios, and wrappers are quite expensive. So you usually do that if you really care about predictive performance. Maybe also you care about producing really small feature sets, which are quite carefully constructed so you can interpret them. But as you will see, these come with considerable computational costs. So this concludes our session here. Again, bye-bye. Hope to see you again in the next session.